Okay, any questions before we start?
We are going to start from
Monday. Continue from Monday lecture. Well, of course, if you have questions about the examples that we did on Wednesday, you can also ask. I mean, if you remember on what we did on Monday, we had basically started discussing the properties of the electric field. We defined the electric field. We first showed that using the superposition principle for an arbitrary charge distribution, we can always write the electric field in this form. Take your, let's say, r prime, rho of r prime, r minus r prime divided by r minus r prime cubed. And now we said that if this is true, then this is nothing but minus the gradient of d cubed r prime, rho of r prime divided by r minus r prime. And we identify this factor over here as our electrostatic potential. So basically, we said that we can always write the electric field as minus the gradient of some scalar function. But this automatically led us to the conclusion that the curl of the electric field is equal to 0. Well, in fact, if you have any vector field whose curl is equal to 0, you can always write it as the gradient of some scalar function. So basically, this is a two-way implication. If one is true, then the other one is also true. And then we said that we looked at the divergence of the electric field, which was d cubed r, rho r prime, rho of r prime, the divergence of this field. But this divergence we had already shown last week that it was equal to 4 pi times the Dirac delta. And hence the divergence of the electric field was equal to 4 pi the density. Now, if you remember these laws from your first year courses, instead of writing the curl of the electric field is equal to 0 in your first year course, we had said that the integral of the electric field over a closed loop was equal to 0 all the time in electrostatics. And instead of writing the Gauss law in this form, we had E dot ds integrated over any closed surface was equal to 4 pi times the enclosed charge. Now, the advantage of writing in differential form is that now it's a local law. The integral is not a local property. You are just summing over the values at different points. But the derivative only depends on the value of a function at a given point and at the nearby point. So it's a local property. So we are basically expressing the laws in terms of as local laws now. Now, the nice thing is, so this has to be satisfied at every point individually, and this curl of E is equal to 0. But we can also know, for example, and these laws tell us how the electric field changes from one point to the other one. So if you know your electric field, let's say at the boundary, if you know that your electric field or some properties of the electric field in the boundary, we will see, and you know the charge distribution inside, only inside, then these two differential equations will allow us to determine what the electric field is at every point. Now, you see, if you want to use this expression, this integral expression over here, you have to know the charge density everywhere. Even if you are just interested in the electric field, let's say in this volume, you have to know the electric field everywhere in order, the charge distribution everywhere in order to write it as an integral, as that integral over there. But now these differential equations would allow us to determine the electric field if we know the value of the electric field, or let's say we will need, in fact, the potential, we will be solving for the potential. If you know the potential at the boundary, and if you only know the charge inside your volume, and that would be enough. You don't need to know what the charge distribution is everywhere on all other places. And most of the time, we do not know what the charge distribution is. quite often the problems we will be studying is there's no free charge in our volume, but on the boundary we put some metals which we connect, or some wires which we connect to some batteries so that we keep their potential at a given value. So we don't know where the charges are, so we don't know the charge distribution. But nevertheless, we will be able to determine the potential everywhere inside our volume, and also hence the electric field inside our volume, without knowing the charge distribution. That will be kind of our eventual aim. And then we said, okay, so we know these differential equations, we know that there is this potential, we could express the work done on a given charge to bring it from infinity to a given point, and we said that the total work done, if we have a collection of charges, then the total work done to bring all these charges from infinity, that will be the energy stored in our system, will be nothing but sum over all the charges, the charge multiplied by the potential created by other charges. So phi I at the position R is Ri is in fact defined as sum over, let's say, J, Qj divided by Ri minus Rj. And J should not be equal to I. So for point charges, this is what we had obtained. And we said that, okay, we can also, let's say here, we have a 1 over 2. Basically, to avoid double counting, we had inserted that 1 over 2. And starting from this expression, we took the continuum limit, and then what we had in the continuum limit, the work done was, we could write it as 1 over 2 dq, well, the qi, what we did is, if we have a continuum limit, we just divide it into very small volumes, and the qi would corresponding to the charge of each one of those volumes, but the charge of that volume is nothing but the charge density multiplied by that very small volume. This is rho of r times d cube r, multiplied by the potential at the point R. And I just had made a warning, if you remember, that here, you see, in these summations, I is equal to J is omitted. Here, let's say I is equal to J is not omitted. Mainly because we define phi of R also as this integral, d cube R prime rho of R prime divided by R minus R prime. So in that integral, there is nothing that prevents R prime to take the value R. If the integral is finite, then fine. Well, this I is equal to J term is in fact, I mean, if you look at the discrete case, it is just the charge squared divided by 0. It is divergent. It is what we call the, well, in the continuum limit, sometimes it is divergent, sometimes it's finite, but what we, this qi over 0 is nothing but the potential created by a charge at its own position, which is divergent. And then we multiply it by the charge to obtain the energy. So it is a property of the charge itself, let's say. And that is what we call the self-energy. Now, when we are talking about all these charges, we are always talking about bringing them one by one. But how much energy did we use to create the point charge? At least in this approach, it just turns out to be an infinite, but nevertheless an infinite constant. And since we will be always dealing with energy differences, if it is infinite, we will just omit it because it won't change. If it is finite, we will just ignore it. Our results will be finite. But again, the important thing is when we take differences, it will not change. It will be eliminated anyway. So it will not influence the physics. And we will see an example of that. Now, then, of course, there's still a problem in this expression. something we do not like, because you see phi is, okay, it is the potential, but it's the potential created at this point by some other charges over there. In that sense, this expression of the energy is not a local expression. Well, it looks local because we are multiplying the charge density at this point by the potential at that point. But at the potential at that point is created, let's say, non-locally. So in that sense, it has some hidden non-locality in it. But we would like to express it in terms of some other local properties. And furthermore, I mean, you see, the charges are always separate. So, I mean, if you are express something in terms of the interaction of different charges, there's no way to avoid that non-locality. So we would rather express this in terms of things that we can actually measure also at every point. I mean, rho we can measure, but measuring phi is kind of problematic in the sense that we only measure potential differences, not the absolute value of the potential. So let's go ahead and try to convert all of these in terms of not the charge density and the potential, but in terms of, for example, electric field. That's something we can do. Now, how to do that? Well, we know what we can relate the charge density and the electric field through the Gauss's theorem. The divergence of the electric field, we had said that it was 4 pi rho. So instead of rho, we can just substitute 1 over 4 pi times the divergence of the electric field. So let's just substitute it over here. This is equal to 1 over 2 d cubed r, well, 1 over 8 pi times the divergence of the electric field times phi of r. Now let me do some integration by parts. I will be integrating by part over here so that, I mean, phi, I want to get rid of phi. The electric field is nice, so I want to, instead of taking the derivative of the electric field, if I take the derivative of phi, that will give me the electric field. So I can convert everything in terms of the electric field. So let us do that. Let me first look at this expression. Can I write it as a total derivative, whose integral will give me 0, because I can convert it into an integral over the volume over the surface at infinity. It will be 0. And a derivative over phi. Well, this is equal to del I ei phi. I'm just using index notation. This will be, I can write it as del I times ei times phi minus ei del I times phi. Well, the first expression is nothing but the divergence of phi times E. Phi times E is a vector field, so I can take its divergence. The second expression is nothing but the gradient of phi multiplied with the electric field. Well, you see, gradient of phi was minus the electric field. So this I can also write as divergence of phi times the electric field plus electric field dot the electric field. So that second term is nice. It doesn't depend on the charge densities. It doesn't depend on phi, the potentials. It only depends on the electric field. The first term is a total derivative. So if I can convert it to a surface integral, when I send the surface to infinity, it will be 0. So the work done to bring a charge configuration or the energy stored in a given charge configuration, I can also write it as 1 over 8 pi d cubed r divergence of phi times E plus 1 over 8 pi d cubed r times the electric field squared. As I promised, the first term is nothing but the surface integral of phi times E plus 1 over 8 pi times d cubed r E squared. Well, let's go back. We are looking at the charge distribution, the energy stored by all the charges, basically. So here the integral over here is over all the charges. So over the whole volume. So this surface is at infinity. So the energy stored in a charge configuration, we can also write it in terms of the electric fields. So basically, in the first expression, it was kind of stating that, okay, the energy stored is in the charges and their interaction, kind of. Well, this expression rather says that energy is not stored in the charges themselves, but in the electric fields created by the charges, which is kind of, let's say, nice. First, it implies that electric field, although we started it as a mathematical definition, it has its own physical properties like the energy. It carries energy just like ordinary particles. And eventually we will see that it also carries momentum. And here everything is local. You can talk about the energy stored, let's say, in any volume. Even if there are no charges there, if there are charges outside, there will be some energy stored in everywhere that has an electric field. And the energy density of the electric field we define as 1 over 8 pi times E squared. So this is how we identify the energy in the electric field. Let's also remember how we had done this derivation in your first year. So first of all, okay, this is our parallel plates. They are separated by a distance d. They have an area A. And d is much, much less than, let's say, square root of A. So it is very thin, or area is very large. So it's almost infinite. So how do we calculate the electric field inside? Well, we will use Gauss law. How?
Say that the electric field from one plate is equal to the charge over in a unit area over 2.
So how do we divide it? How do we derive it? Now, we will basically use the Gauss law. We will use this one in this form. Now, first, before continuing, let's look at any surface, in fact. Any charged surface. And then we can just imagine, to be able to use this law, first we have to kind of take some Gauss surface. And we can just imagine a cylinder, a very small one. So this tells me that E dot, well, let me enlarge it a bit. If I enlarge that segment, I will eventually take the limit that that surface, that volume goes to 0, both the cross-section and the height will go to 0. So in that limit, the piece that is inside my volume, the surface that is inside my volume will be it will look almost flat. And so I take this perpendicular volume, perpendicular cylinder. Secondly, I will assume that the charge density at that point, the surface charge density at that point is sigma r. R is being the point inside my volume, and it will remain inside my volume even in the limit when I take the size of the volume to 0. So that is the point R. So there is so where is ds? What is ds over here? Here the ds is, I can choose it to be pointing upward. Here ds will be pointing downward. On the sides it will be perpendicular to my surface. Basically at every point ds is different. So this E dot ds I can write this ds to be its magnitude in the normal direction. And again, this normal direction will change depending on where I am. So this is E dot dn multiplied with ds from over this closed loop surface. Now I can divide this integral into three parts. E dot n times ds over the top, E dot n dot ds over the bottom, E dot n ds over the sides. Now, I'm going to take the limit as volume goes to 0. So let's say this is the height h, this has a total area A. First, to take the volume to 0, first let's take A, very small but finite. Then h goes to 0. Well, if I take the h go to 0, then this integral over the sides it goes to 0. Now Q enclosed here is nothing but sigma at the position R times A. Well, in our notation this semester we don't have this epsilon 0, we have 4 pi over here. So basically, in the limit h goes to 0, 4 pi sigma r A is equal to E dot n over the top plus E dot n over the bottom. Well, I am considering A to be very, very small. Not yet 0, but very small, almost there. But if A is very, very small, then the electric field, well, we are expecting it to be continuous on the top and on the bottom. It need not be continuous from the top to the bottom because there is a surface it can change the electric field very fast. We don't know. But at every point, between a point on the top surface and the nearby point, there is nothing that would cause the electric field to change. So electric field at the top is continuous. Electric field at the bottom is continuous. Only maybe across the boundary there might be some discontinuity. We don't know. We will discover it. So if that is the case, then E dot dn over my surface is almost a constant. So 4 pi A times sigma r will be E dot n evaluated at some point on the top times A plus E dot n evaluated at some point at the bottom times A. Well, now A is cancelled from both sides. Now I can take the limit as A goes to 0. And also keep in mind that n at the top is equal to minus n at the bottom. Because if you go back to our figure, n at the top is pointing in that direction, n at the top bottom is pointing in the opposite direction. I'm considering a cylinder. So 4 pi times sigma r is equal to E at the top minus E at the bottom dot n. Let me just call this n, the normal vector at the top. So this is, n is the normal vector, a unit vector. So when we take a vector and take its scalar product with a unit vector, what we obtain is just a component in that vector. So this basically in that direction. So this basically tells me that the electric field across this surface is not continuous. There's a discontinuity given by the surface charge density, that is the charge per unit area. Note that the sigma is not the volume charge density, but the surface charge density. It's the charge per area. So this will be one of the things that we will be using quite often. And top and bottom are determined by the direction of n. So n vector points from bottom to top. So you could have just chosen the n vector to be in the opposite direction. It doesn't really make any difference, but you also have to change the identification of top and bottom. And this is, by the way, a result that is valid for any surface. We didn't make any assumption on the shape of the surface. Any surface that is sufficiently smooth, so that if you look at from very, very close by, if you look at a very, very small region, that region, no matter where it is on the surface, that region is flat. Now let's apply this to our problem. This is the problem we have. So we said, okay, we didn't say it, but let's say there is a charge over, plus Q charge over here, there is a minus Q charge over here. So here there is a surface charge density plus sigma, let's say. Here there is a surface charge density minus sigma, where the sigma is Q over A. Now what else do we know? If you look at the charge distribution, well, it is quite symmetric. But assuming it is infinitely long, in fact, the electric field should be vertical everywhere. Because there is no preferred direction, the electric fields cannot bend to one direction or the other one. So the electric fields everywhere will be just perpendicular to our surface. Assuming, of course, there are no other charges around. Or in fact, let's just do it this way. Let's say the electric field is E1, the electric field is E2, the electric field inside is E. For the timing, I'm not making any assumption about E1, E2, or E. Now, I have this condition now. Let us choose the n vector to be in this direction. Now, E top, if I apply this to this boundary, to the top boundary, E top is, what is E top? E1. E bottom? E bottom is E, not E2. You see, I'm looking at this boundary over here. I'm looking at that boundary. Okay? Minus E dot n. This should be equal to 4 pi sigma. Well, let's look at the bottom boundary. This one, the bottom one. What is E? I still use the same n vector. What is E top? E top is now E. E bottom? E2. Scalar in the direction of n, in the perpendicular direction, this is equal to 4 minus 4 pi sigma, let's say. Well, this tells me, this is what the Gauss law tells me. Gauss law doesn't tell me anything more than this. But this only implies that E1 is equal to E2. That's basically the only thing I know. Now okay, this is not the result that you had obtained in your first year. Because in your first year, you made additional assumptions. Now, one assumption was that, well, this E1, E2 is basically the electric field created by some other charges nearby. So if there are no other charges except on your plates, then this E1 and E2, they will be zero. Now the second assumption, well, not really the assumption, E1, E2 is equal to 0. And then, again, this only tells you that E dot n is just minus 4 pi sigma. Even if we just set E1 and E2 equal to 0. Then there is an additional input. You say that, okay, this is almost infinite, so there's no preferred direction, so the electric field should be vertical. It cannot have any other direction. So basically you said that E is equal to some number in the n direction. This is the additional input you give to the Gauss law. Then under these conditions, just E is equal to minus 4 pi sigma. So the electric field is minus 4 pi sigma. And so it's basically in the opposite direction to n. So this is our electric field. It's uniform, it's constant, etc. So one key thing is, without these additional inputs, you cannot really tell what the electric field is. You need some additional input. That will be basically our boundary conditions. Okay, if you remember in your first year, I was, at least for these guys, I was insisting that you should explain how you choose the Gauss law, how you take the integral of Gauss integral, etc. So this is basically the reason. Without those assumptions, without first knowing something about the electric field itself, I mean, this law is always valid, it's always true, but not always useful. Okay, so finally we have the electric field. And this we should write as minus the gradient of some function. Well, let's just choose this as our z-axis, as our coordinates. Well, the simplest choice would be this is equal to phi is equal to 4 pi sigma z. This is our electrostatic potential. If you take the gradient, it is a vector in the z direction. Well, z direction is nothing but our n vector. So we identified the potential. Now we can write the total energy stored. Total energy stored is 1 over 2 q plus times phi plus q minus times phi minus. Remember, the energy stored we had written as 1 over 2 sum over all charges. Here it was point charges, but nevertheless we can sum the charges located on conductors because they will all have the same phi. So that's basically what I did over here. So this is equal to 1 over 2. The total charge in the plus plate is q. Well, let me also choose this point as z is equal to 0, where its separation was d. So the potential at the plus plate is 4 pi sigma times d plus q minus is minus q Well, the potential at the minus plate, I just set it to 0 by setting z equal to 0. So this is the energy stored. 2 pi q times sigma times t. Now let's convert these in terms of the electric field. First of all, instead of sigma, I can just write, or instead of q, I can write sigma times area times d. Well, sigma, you see if you go back here, sigma is nothing but minus E over 4 pi. So we can relate the charge, then surface charge density to the electric field. 2 pi times minus E over 4 pi squared. Well, A times D is nothing but the volume where the electric field is non-zero. This is equal to 2 pi over 16 pi squared E squared times V, or 1 over 8 pi times E squared times V. And then in your first year we had said that, okay, let's define this as the charge density inside our capacitor, which is uniform, times V. Of course, in this derivation we made many approximations, many assumptions. First of all, we assume that this capacitor is almost infinite, although we took it to have a finite volume, and hence ignored fringing effects. The electric field will not be uniform as you go to the size of the capacitor. We ignored those effects. Furthermore, since by ignoring that, we assumed the electric field was uniform everywhere. So under those assumptions, this result is correct. Now the problem is how crucial are those assumptions in this derivation. So we didn't really know whether this, we could identify 1 over 8 pi E squared as the energy density stored in the electric field in the more general circumstances, where you might not have any plates to start with. You can have any charge distribution, you can have non-uniform electric fields, etc. We didn't know whether it was true or not. But now, the derivation we had done before this example over here, we didn't make any assumption, any charge distribution. For any charge distribution, this is the energy density. And the energy stored in our charge distribution is in fact energy stored in the electric field, which had an energy density given by this expression.
Can you go back to the capacitors? So when you took the Gaussian surface to be the first order,
Okay.
and then we calculated the E. Isn't that the E only due to that boundary without
E.
taking into account?
Well, we don't really know. I mean, you see, you can have put a capacitor over here and then put some charges over here. If you put some charges over here, they will create an electric field. They will also create and contribute to the electric field between these plates, because the total electric field between the plates will be the one created by these sigmas, which we assume to be uniform, plus the electric field created by these other charges. That is what we call the superposition principle. So this E need not be created by sigma only.
What I mean is that is the E we found created by only the plus sigma or the plus and minus sigma?
Plus n minus sigma.
How is that possible? We did not include the second surface inside our question.
Well, we don't need to. You see, if you look at the Gauss law, if you look at this Gauss law, so what it tells you is that take the electric field created by all the charges, everything. Imagine a surface. Integrate this electric field over this surface. This is the remember, this is the electric field created by every charge. This integral only depends on the charge inside my surface. This is what the Gauss law is. It doesn't depend on the charges out of my surface, although the electric field does depend on the charges outside my surface. So it's just the contribution to the electric field due to the charges outside my surface, they just be, in the integral, they just go to 0. Now, okay, so this is kind of, let's say, the power of the Gauss law. The integral depends only on the charge inside, although the electric field that we are integrating over depends on everything. Now, a more specific example to your question. You see here what we are actually doing. Let's look at only the plus sigma charge. Well, it will create an electric field in both directions. Similarly, we can take the minus sigma plate. It will also create an electric field in both sides. And each one of them will create an electric field that will be 2 pi sigma. That will have a magnitude 2 pi sigma. Now, when I put them together, the electric field here just cancels. So in between, I obtain an electric field whose magnitude is 4 pi sigma. Now, in the above derivation, in a sense, yes, you're right, in our Gauss surface, we didn't take the bottom part, but we said that, okay, above my plus sigma plate, the electric field is 0. Why? Because of the bottom plate. So indirectly, we are already taking that effect into account. If I only have the plus sigma plate, it creates an electric field in both sides, not just one side. But again, the more important thing that you should understand is that here, the electric field in Gauss law is the electric field created by all the charges, not the charges inside the surface. Whereas the integral, the surface integral, only depends on the charges inside my surface. It doesn't depend on what charges I have out of my surface. Any other questions? So let's give a break now, and we will continue in the next hour.